Okay, so we can discuss motion of a car on a banked curved road in detail. So whenever a car moves on a banked curved road, the forces acting on the car will be the normal reaction force N and the weight of the car mg. Apart from this, frictional force will act on the car and it will be acting along this direction, opposing the motion of the car. And it will be more clear in the next figure. See, car is moving on the banked road. See, only this portion of the car has been represented here. This portion of the road actually is represented here because this portion of the road is slightly raised with respect to the inner edge, this portion of the road. So only this part of the road is represented in this figure. Okay. Now the car is moving on such a banked road. So the forces acting on the car is the normal reaction mg, weight of the car vertically downwards. Then frictional force act on the car, which opposes the motion of the car because car will move in this way and the frictional force will opposes that movement of the car. And apart from the centripetal forces which acts towards the center along this direction. Okay, and theta, this angle theta is the angle of banking. And here you can see the three vectors, that means the three forces, the normal reaction, mg and the frictional force are acting along different directions. So we can't add them simply like numbers. Since they are vectors, we need to go for a vector resolution. So we can resolve vector n first. Whenever vector n is resolved, we get two mutually perpendicular components, and this component which is adjacent to angle theta is n cos theta, and this component is n sin theta, and these two components are mutually perpendicular. So n is resolved into n sin theta and n cos theta. Next, similarly we can resolve vector f, and this component which is adjacent to theta is f cos theta, and this component is f sin theta. Also by geometry, if this angle is theta, then this angle will be theta by geometry of figure. And similarly, if this angle is theta, then this angle also will be theta. Okay, and you can consider this case here in the case of alternate or opposite angles. Okay, if this angle is theta, then this angle also will be theta. Now, which are the forces acting along the vertical direction now? Now we can see some forces acting along the same direction. So if we look at the vertical axis or y-axis, the forces acting along y-axis are n cos theta, f sin theta and mg. So we can say this n cos theta is balanced by f sin theta and mg. That means n cos theta is equal to f sin theta plus mg. So that is written here in the vertical direction, n cos theta is equal to f sin theta plus mg. And which are the forces acting along the horizontal direction? That means along the x-axis. So here you can see n sin theta, f cos theta, and one more force act along this direction, which is that centripetal force mv square by r. So we can write this n sin theta plus f cos theta is balanced by our centripetal force mv square by r. Okay, so that is what is written here, n sin theta plus f cos theta equal to mv square by r. Next, we know that the force of friction F is equal to mu s into n. So next is to substitute F is equal to mu s into n in equation number 1 and 2. So equation becomes n cos theta equal to, instead of F, substitute mu s into n. So mu s into n sin theta plus mg. And when you rearrange this, bring mu s n sin theta to LHS, you will get n cos theta minus mu s n sin theta equal to mg. And from this, take n as common factor. So whenever you take n as a common factor, you will get n into cos theta minus mu s sin theta. Okay, so here n is the common factor. So n into cos theta minus mu s sine theta equal to mg. So therefore n is equal to mg by cos theta minus mu s sine theta. Okay, so that is what is written here. And again, when we put the value of n in the equation number 2, you will get mu s n cos theta plus n sin theta equal to mv square by r. So which is equation number 2, my dear children? So this is our equation number 2, and in this equation substitute f is equal to mu s n. So you will get mu s n cos theta plus n sin theta equal to mv square by r. Okay, that is written here, mu s n cos theta plus n sin theta equal to mv square by r. And again in this equation substitute this value of n equal to mg by cos theta minus mu s sin theta. This expression you should substitute here for n. So when you substitute, you will get mu s into, instead of n, mg by cos theta minus mu sin theta, and cos theta is here, so you will get cos theta plus, again for n substitute, mg by cos theta minus mu sin theta into sin theta equal to mv square by r. Okay, now here in the numerator part, mg is common, isn't it? So you can take mg as a common factor. You can directly add the numerator part. Why? Just look at the denominator part. Denominator of this term is cos theta minus mu sin theta. Denominator of this term is cos theta minus mu sin theta. So if denominators are same, you can directly add the numerator. So this is the numerator, mu s mg cos theta, and this is the numerator of second term, mg sin theta. So in both the terms mg is common, so take it outside. Then what is left? Here we are left with mu s cos theta, and in the second term we are left with sin theta. So you will get mg into mu s cos theta plus sin theta by the denominator, which is the common denominator, cos theta minus mu s sin theta, equal to mv square by r. So this is the expression. And again here in this expression you need to divide the numerator and denominator by cos theta. So this is the numerator part. Here divide by cos theta, and again here also divide each term by cos theta. And this is the denominator part. Here also divide by cos theta, cos theta. So you will get another expression. Here you will get mg into cos sin theta by cos theta is tan theta, plus here cos theta by cos theta, it will be cancelled, plus mu s divided by, in the denominator we have cos theta 1 minus mu s sin theta by cos theta is tan theta. Okay, that is the LHS part, and equal to mv square by r. So that is what is written in the next slide, mg into tan theta plus mu s by 1 minus mu s tan theta equal to mv square by r. Okay, now again you need to find out the expression for v square. So here when you divided each term with cos theta, you got mg into tan theta plus mu s by 1 minus mu s tan theta equal to mv square by r, isn't it? So here we have m, here we have m, like factors will be cancelled. Then we are left with v square by r here. You need to find out the expression for v square. So from this you will get v square equal to rg into tan theta plus mu s by 1 minus mu s tan theta. Okay, this is v square, then v will be square root of this expression. So that is what is written in the next slide. So v square equal to rg into tan theta plus mu s by 1 minus mu s tan theta. Therefore v equal to square root of rg into tan theta plus mu s by 1 minus mu s tan theta. So this is the maximum speed of the car on a banked curved road. You must remember this expression. Okay. Now there is a special case. When the velocity of the car is equal to VO, VO means optimum velocity. So whenever the velocity of the car is equal to optimum velocity, there won't be any unnecessary friction, because optimum speed is the speed at which a vehicle can move over a curved banked road without using unnecessary friction. So the frictional term will be 0. When the car is moving with the optimum speed, the frictional term can be taken as 0. So in this expression, mu(s) term stands for friction, and that mu(s) term can be taken as 0. So when you substitute mu(s) equal to 0 in this expression, you will get V equal to square root of Rg into tan theta, because here mu(s) will be 0, and whenever you substitute mu(s) 0 here, this term will be 0, and 1 minus 0 will be 1. So you will get V equal to square root of Rg into tan theta, and this is the expression for optimum speed. And at this optimum speed, there won't be unnecessary friction, so there will be little wear and tear of the tires. Okay, so that's all about the motion of a car on a banked curved road. Then there is a numerical based on this. A circular racetrack of radius 300 meter is banked at an angle of 15 degree. So the radius of the circular track is 300 meter. Angle of banking theta is 15 degree. If the coefficient of friction between the wheels of a race car and the road, that means mu(s), is 0.2, what is the optimum speed of the race car to avoid wear and tear on its tires? Okay, what is the expression for optimum speed? Optimum speed expression is V equal to square root of Rg tan theta. So here radius Rg tan theta, radius is given 300, G 9.8, theta is given 15 degree. So just substitute, and the value of tan 15 is obtained from the logarithmic table, Clark's table. From the Clark's table you can easily find out the value of tan 15, and you will get the velocity as 28.1 meter per second. And second part of the question is, you must find out the maximum permissible speed to avoid slipping. So what is the maximum speed possible? This is the maximum speed. V equal to square root of Rg into tan theta plus mu(s) by 1 minus mu(s) tan theta. So here substitute. So you will get square root of 300 into 9.8 into 0.2 plus tan 15 by 1 minus 0.2 plus tan 15, because the coefficient of friction is 0.2, and after simplification you will get the value as 38.1 meter per second. Okay, so like this you are supposed to solve the problems based on this banking of roads. Children, that's all for today's session. Notes of the topic and YouTube video have been uploaded, just go through it. We will meet in the next session. Till then, take care all of you. Stay home, stay safe. Keep learning. Thank you.